you for the introduction, and thank you for having me here today. So as Alexei was saying, so I'm an experimentalist. I work in an experimental group that, work in multimode quantum optics. The idea is to exploit multimode light to study fundamental phenomena, but also to eventually build some quantum technology. So today, in particular, I'm going to speak about a proposal which we made with some collaborator in Palma de Mallorca in Turku University to build a quantum complex network. And I will explain a little bit what I mean with complex in this context later. And so I just want to spot the two people that really made the work, so Francesco Anzani and Johannes Nokkala. So here the outline of my talk. I will start by giving some idea of what we can do, so how our experiment works. And in particular, well, you speak about multimode quantum optics. In our case, especially in the last 10 years, we were more working with multimode in the spectral and temporal domain. So light with particular shape in the spectrum and in the temporal domain. Well, then I will go towards some kind of quantum network. So the idea is that here, well, you see it's a very long title, which really seems something which is theoretical, and in a way it is, in the sense that the idea is that as we deal with the Gaussian process, we have a very well-known method to simply describe what is going on. And also what we are able to do is to control the simple optical component of this way of describing our state. So, and here, while we have a very good control, we can generate any kind of network, stay in the Gaussian regime. And in particular, I will go towards this cluster state generation, and more generally, quantum complex network. Here, complex mostly refer on the topology of the network that we have. And in particular, I'm going to show how we can engineer a reservoir and its probing in this context. So let's start with the multimode quantum optics. So the main idea of our group is to merge optical frequency comb with quantum optics. So optical frequency comb are femtosecond mode dot laser. So you can describe them in the temporal domain as strain of pulses, and then in the frequency domain as a comb in which you have many, many components. And the idea is to merge it with a very simple quantum process, which is the parametric process, which is a well-known process in which one photon, blue photon, can be converted into Dr. photon, for example. But we look at it in the continuous variable regime, so we look at amplitude of phase of the output field. So what you can have in this case, so sometimes we have cavity around the process in order to enhance the process. In the degenerate case, what you get at the output are squeezed state of light, so you have statistic below the shot noise. And then if you are in the non-degenerate case, so the two frequency of the two field output are different, for example, you can have a quadrature entangled state. So when you merge the two things, which means that, for example, you have a comb, which is the pump of your process, so you have many frequencies entering in your process. So this is a picture of one of the experimental setup, where it's a scheme. Of course, it's not really a picture of the one of the experimental setup that we have in the group. What is going on is that you have a multimode process. So, for example, if you just consider one of the frequency of the pumps, this can give you some entanglement at two down-converted frequency, the yellow, the green. But then this yellow can be also entangled with a third one by considering a second component of the pump. And then you can have a third component that is going to entangle this one with a fourth component and so on. So if you consider all the possible combination that you can get from all the components of the pump, what you obtain for the down-converted spectrum is a non-trivial entanglement structure. So the idea is that we want to, you can measure the entanglement in that case, or at least try to characterize the entanglement by trying to access, we cannot really access each tooth of this comb, but we can access frequency bands. And so we are going to see what is going in this frequency band. So how we can look at entanglement? So the main idea is that we use homodyne detection because we want to see an entanglement in continuous variable regime. So in homodynamic detection, you can measure the quadrature by mixing your state with a local oscillator, strong coherent field, then you the 50-50 beam splitter, and then you make the difference at the output by 2 photodiodes, and then this is exactly the measure of X and P. So the homodynamic detection is an interferometric method. That means that you can select the modes in which you want to measure the quadrature. So in particular, I can select one frequency band, for example, the yellow one, and this is just by sending the yellow band as in the local oscillator. But I can also choose some more particular complex spectrum that define a particular mode. And then I'm going to look at the quadrature in these modes. We can also do something more, which is a multi-mode homodynamic detection, in which we can simultaneously measure all the quadrature at different frequency bands. So the idea is the following. You mix actually your system again with the local oscillator, and after the mixing, we can disperse the different wavelengths, and then couple the same wavelength is focused on 2 particular photodiodes, and then you have a couple of photodiodes, the same wavelength that are detecting a particular quadrature. And then, in this way, you can have simultaneous measurement of quadrature at all the different bandwidth of the system. And then, as I was saying before, the process that we are looking at here are characterized by Gaussian statistics. So that means that you just need covariance metrics to characterize them. So here, I'm just showing these are experimental data. These are 2 covariance matrices for the amplitude and for the phase, so for X and P. And you have, the different frequency bands on the row and on the line. And what you have actually in the diagonal part, you have the variance of the particular wavelength, so you can get information of having squeezing or not. So actually here is renormalized in a way that 0 is the shot noise limit, so here you can see that you have something which is below the shot noise limit, so you have some squeezing. And then the off-diagonal terms gives you the correlation. So this gives you the EPR correlation, so the kind of entanglement that you have between different wavelengths, different colors. Well, in that case, as you have square metrics, you can think about having a diagonalization procedure. So in principle, you start from this matrix and you get a diagonal one. And the basis change that give us the diagonal matrix in our system, this particular case, corresponds to a basis change from frequency base to emit-Gauss modes in frequency. So that means that as in that case you have just a diagonal covariance matrix, you have independent modes. So our system can be described in this basis as a collection of independent modes with no correlation, which are squeezed, or in the wavelength basis as a system in which you can find entanglement. So this global basis change can change actually the entanglement characteristic of our system, can be exploited to do some quantum protocol. Okay, that of course corresponds to the diagonalization of the Hamiltonian that describes the multimode parametric process. Well, okay, I was speaking about EPR correlation. Maybe the covariance matrix is not enough to convince you that we have entanglement in this system. Actually, what has been done in the system is to test a particular multipartite entanglement criteria. And in particular, if you take, for example, the whole spectrum at the output and you divide it in 10 frequency band, and you try to look at all the possible partition, which are something like more than 100,000 partition, and try to look if you have entanglement between them, you see that all are non-separable according to this criteria. So really we are in the case of a multipartite entangled state. Okay, that's it. So that's the kind of resource that we have. And now I want to go a little bit more in the detail how we can build a particular kind of network with this resource. So I was speaking about the fact that we have entanglement or just squeezing by making a basis change. So here I'm just going to something which is more specific, which is the Bloch-Messiah decomposition that holds for all symplectic transformations. So in particular, imagine that you have process in which in any case, what you have, you maintain the Gaussian statistic of your state. So all this process can be depicted as having a collection of input modes, which undergoes a basis change, then a squeezing, a multimode squeezing transformation, then another basis change. So in the spatial domain, this corresponds as having input modes that go into a multiport interferometer, and then in each mode you have squeezing, and then you have again another multiport interferometer. So the multiport interferometer in our case is the basis change in the frequency domain, because we are multimodes in the frequency domain. So here is a general case in which you have the spatial domain. And also in our case, what we have is that at the input we have a vacuum state. So at the frequency that we look for the up-converted modes, at the input we have vacuum state. So that means that the first basis change can be discarded, because, I mean, if you just have a vacuum entering a multiport interferometer, the output you have vacuum again. So, I mean, something that is not important. So, I mean, all the process in this case is described by just squeezing and one basis change. So this is a different way, can give us a different way of looking at what I was saying before about the covariance metrics, in the sense that we can interpret our experiment as if you have squeezing in what we call the supermode basis, so the basis of modes in which actually the Hamiltonian was diagonal, so in which you have squeezing. And then we detect actually our system, we measure our system in a different basis, which is the one given by the wavelength, the pixel basis. And for going to one to the other, we have a basis change. So in a way, you have a quite intrinsic way of describing what is going on in the process by considering the Bloch-Messiah reduction. Well, that's interesting what we can do with that. So the idea is that we can map any kind of Gaussian symplectic process with these two operations. Sorry, this and this one. Or the third one, if you are not, and also the third one if you are not starting with vacuum state. So how we can exploit it for build particular state, for example, cluster state. So cluster state are a resource in measure-based quantum computing. Here I consider a continuous variable case in which, I mean, normal ideal builds consider a collection of modes which are infinitely squeezed in the P quadrature, and then you apply CZ gates, so entangling gates between different modes. So the way you depict them is having a collection of modes, and then you have the link, which are the entanglement connection that you create between them. And these are useful for measure-based quantum computing, and actually the way you build it is our symplectic Gaussian transformation. So in a way, they can be depicted as just these two operations. So you just need to control some squeezing and some basis change in order to build it. And in our experimental setup, actually, what we can do is just consider, okay, of course, you cannot have infinitely p-squeeze state. You consider finite squeezing for different modes. And then, for example, you can just consider the supermode basis in which we have some squeezing, and then apply a particular basis change by measurement, which gives us a particular shape which corresponds to a cluster. This is what has been, so this blue part is actually the measurement basis, I mean, the basis change that is described by the measurement. And what has been demonstrated that we can build different kind of cluster with different geometry. So this method is quite versatile for building different topology of cluster. Actually, the number of modes that can be involved up to now are something like 12, which are not so many, but it's really completely versatile in the sense you can really choose the shape of correlation that you can have. Of course, I had to cite, I mean, we're not the only group able to build cluster state in continuous variable regime, and actually, I mean, the record in number of modes has been reached in the group of Furuzawa using temporal modes. They had something like 1 million of modes, sorry, 1 million, not billion, which are entangled in a cluster. Okay, so this is I mean, a kind of example, so a kind of network. I mean, cluster state can be seen as a network that can be built in our setup. Now I want to go more in detail in what we want to do with quantum complex network and how we can implement them in our setup. So first of all, I want to use a quite general definition of quantum complex network, which is a collection of quantum systems arranged in a non-regular topology. So as I was saying before, complex here refers to the topology of the network. So here you have one of, I mean, for example, random network. You can have different kind of topology. Here I'm considering, for example, linear chain with shortcut. It has more word network. You can have network with community structure. So more in general, complex networks are actually described by the statistic of their links. I mean, you don't have a regular geometry that you repeat, but you have a particular rule for the statistics, how the link, how the network grows, how one node is linked to the other, and so on. And then you can ask why, I mean, complex networks in the quantum regime are interesting. So this is my personal answer. So of course, when you just start with complex network and you add some quantum property, you have something which is different from the classical one. So in a general case, you can ascribe phenomena as localization, quantum walk, phase transition, quantum transport, and particular kind of synchronization to this scenario, actually. And then, of course, we are interested in quantum network with no classical equivalent. So, for example, the one in which you have entanglement connection between the nodes. And I think they are relevant for the future quantum communication information technology in the sense that you have not to care only about computational complexity, but also about complex topology. Because, for example, if you think about the possibility of having at a certain point a quantum Google, and you think how the classical Google is built, you have a complex topology. And then also, this is something that I'm going to hear today, is more about the fact that quantum complex network can be used to depict the reservoir in an open system scenario. So, and you can think about having reservoir engineering and trying to see how different kind of complex network can interact with the quantum system that you are interested about. So I want to give you a slide on that part, in the sense what we are trying to look at and why they could be interesting, and then I will go more in detail on this third one. So here I'm considering a collection of quantum systems with entanglement connection. So before I was considering the fact, I mean, the generation of cluster states. So in cluster state, you have universal geometry that can be used for making measurement-based quantum computing. And I'm considering to go to more general graph state with entanglement connection, which has complex topology. And first, because, I mean, you can think about, as I was saying before, which kind of shape are going to emerge when we are going to grow quantum network. As I was saying before, Google, communication network. You can consider the scenario of, I think, for example, distributed quantum computing, in which you think that at a certain point you have some servers somewhere, and then you have kind of other clients, which are classical. We try to ask some quantum protocol to the server, and so on. So I think they are relevant really in the way we think that in the future we can have a quantum network that can be used for quantum communication and quantum information technology. And then you can ask which kind of shape are the most resilient against error and failure. So of course, I mean, this topic, it's really close to the topological code, for example, for making error correction topic. But we are going to look at it from a different point of view. That is to start from classical network that we know that are resilient for some particular property, and trying to test in the quantum regime, not really look at the topological code that work for the error connecting. And for example, what we are looking at are quantum communication task. So like, for example, entanglement percolation, imagine that you have a network with a complex shape with different players, and you have not maximally entangled states in this network, and you want to reduce to a particular condition in which, for example, you have good entanglement between two nodes, or you have a particular shape, for example, this shape that can be used to make a protocol like secret sharing with multiplayer. And well, this kind of entanglement, percolation, and concentration depends on what you are looking at exactly, has been actually studied in the DV regime. We have also some results in the CV, but there is no really intensive research on considering different kind of complex network in that case. And really, I mean, the idea is that you can think that you have classical network, for example, the one with scale-free small world behavior that are resilient, that we know that are more resilient. And you can think if the same network can be used in the quantum domain. And for example, I mean, in this paper, it's shown that when you make entanglement percolation, I mean, it's going to be worse and worse when you increase the distance between nodes. And as, for example, the small world network, you have effectively a small world in which all the nodes are connected with each other. I mean, you can think that this kind of network could be more resilient for making this kind of protocols. Okay, so this is more about the kind of quantum network with entanglement connection. And now I go more on the proposal for the reconfigurable optical implementation of complex network, quantum network in our case, in which actually I'm considering more general case, not entanglement connection, but a form of spring-like coupling, which is more general because in the spring-like you can have also the entanglement case inside. So the idea is that we are considering harmonic oscillators, as we have mode of light, and a spring-like coupling between them. What we promise is to have reconfigurable coupling and topology for this network, and to have a relevant size. So the idea is to go up to something like 50 nodes, because when you speak about complex network, I mean, if you have just 1, 2, 3 nodes, well, the complexity is not really something that you can speak about in that case. Here, for example, I'm just considering 3 particular cases, so 3 different networks. So this is not really complex. It's a periodic network in which every third link you reduce by half the strength of the coupling between the nodes. Here you have a linear chain in which you have actually some shortcuts somewhere. And this is for one of the possible random networks that you can define in complex geometry. Well, if you look at the network dynamics, you have spring-like coupling between different networks. So this is kind of the Hamiltonian of the network. It's not really complicated Hamiltonian. You have adjacency matrix in which you have the coupling, for example, between the different terms. And then, well, you can use the normal Bohr basis for this kind of Hamiltonian. And then you can describe the dynamics in the quadrature, so amplitude phase or position and momentum operator of the oscillator, starting at time t, starting from time 0. So here I'm considering 2 different pictures. In this one, we consider how, I mean, the real oscillator depends on the normal modes at time 0, or how they, for example, here depends on I mean, their value at time 0 directly. So I'm not going to say to you what is here inside, but as we have spring-like coupling, you can think that we have symplectic transformation, Gaussian transformation that you can calculate, actually. Here, for example, if you consider the 3 network, the 3 different networks that I was showing before, you can see how, I mean, this transformation evolved during time. You see that you have different transformation during time that depends just on the different geometry, topology that we are considering. And then if you consider just one given time, you can think about, as I was saying before, there are symplectic transformation, they're changing the Gaussian characteristic of your state. You can think about make a Bloch-Messiah reduction of this transformation. So here you have the tree matrix that corresponds to the first basis change. Here you have the squeezing term, so it's diagonal in the quadrature picture. And then here you have another basis change. And then, for example, just consider the fact that you can start with vacuum state, which means that, I mean, you can discard the second matrix. So the idea is that if you want to emulate this particular network, its dynamics at this time t, you have to be able to reproduce these two operations, so the multimode squeezing and the basis change, which are different from the other different for different network at different time. So actually, how we can do that in our experiment, so the idea is that we can have experimental control of the squeezing term via pump shaping. So actually, the kind of squeezing that you can have depends on the nonlinear process that you have inside the cavity. And this nonlinear process depends on the shape of the pump that you send. So you can try to control exactly the value that you get for squeezing for the different modes by changing the pump. And this can be done via an optimization procedure, which is based on an evolutionary algorithm. And okay, so this can be done with the pump shaping, and the control on the other part, which is the basis change, can be done directly by choosing the measurement base as before, for the cluster state. In particular, here is even more simple in the sense that imagine that you want to know what is going on for a particular oscillator of the network at a particular time. So you make the Bloch-Messiah decomposition, then you implement the squeezing parameter as via pump shaping, and then, I mean, you have just to choose the particular row that correspond to the mode that depicts actually this particular harmonic oscillator, and this gives you actually the superposition, the particular superposition of supermodes, which gives you a particular shape that you have to send in order to check, I mean, the dynamic of this oscillator at this particular time. So, I mean, it's just a matter of defining which kind of shape you have to send as a local oscillator. So these are actually the simulation based on experimental parameter of what we can do. For example, here I'm considering the periodic network at 4 different times. So in the upper part, you have the squeezing. Actually, the theoretical value are in red. So the one that I need, I mean, that comes from the Bloch-Messiah decomposition of the dynamics at that time. And in blue, what we can get considering the experimental parameter. And on the lower part, you have the shape that you had to send as a local oscillator in order to check one particular harmonic oscillator of the chain. Which, I mean, I just choose one, which is the 26th over 50. And here you have actually the same, so the other are just the same at different time of the evolution. So this is for the periodic network. This, for example, is for the random network. And of course, you can use actually this emulation in order to get mean value. For example, here I'm just showing the mean value of the excitation for all the oscillator of the network at a particular time, say this time. So I think in black you have the theoretical value, and in brown is what you can get, I mean, if you simulate our experimental setup. Actually, I think the difference is something like 5% of difference maximum between the theoretical value and what we can simulate. Then, okay, what is going on if the dynamics that we want to emulate doesn't start from vacuum? Because I was saying that we are able just to control in our system this term, the squeezing and the second basis change as we start from vacuum. Well, there are 2 cases that can be simply done, which is just the case in which actually you want to initialize the state of the oscillator in a state which is pure and Gaussian, still with Gaussian statistic, Well, in that case, you can just include the generation of this state in the dynamics. And then you have another case, for example, if you want to have a thermal state, well, the idea is that it's more expensive because you have to start with a larger multimode entangled state with double size, and then you have to trace over half of the mode in order to obtain some particular, thermal state. And then you can have all the combination between these two. Okay, so what we can do with this? So I was sure that we can reproduce, in principle, the dynamic of different complex network in our setup. The idea is that we can use that for example, testing a particular probing scheme for reservoir. So the idea is that you have these complex networks, which are a reservoir for a quantum system. And actually, the idea is that in that case, you want to use this quantum system as a probe in order to see the different characteristics of the three different networks. So in particular, the idea here is to probe the spectral density of the environmental coupling. So which gives you an idea in the spectral domain how actually the system dissipates its energy to this reservoir. So here you have the analytical calculation of the spectral density for the three different cases that I was showing before. And well, the idea is that if you look at the probe, the mean value of the probe excitation number, you can recover an information on the spectral density. What you have to do is to change, in order to get all the spectrum, you have to change frequency of this probe, and then looking at its mean excitation number, and you can recover the J of omega, this particular frequency. If you describe actually the system, which is our network plus this probe, and their interaction. So again, we consider an interaction which is quadratic, so it's a Gaussian process. As I was saying before, here again you can have a symplectic evolution of the probe plus the now we call the environment. And if we want to emulate these dynamics in order to get information about the environment, we cannot start with a vacuum state here, because you need some exchange of energy between the two. So this is the case in which actually we have to prepare, at least for example, the probe in an initial non-vacuum state. So we can just decide to prepare in a squeeze state, in which you have some mean photon number. And then you can include actually this part of generation of the state in the evolution. So you consider an effective symplectic transformation, and then you can make Bloch-Messiah decomposition of that, and considering just the two terms that we can control. So as I was saying before, what you have to do is to choose a frequency of the probe, implement the particular Bloch-Messiah which corresponds to this frequency, then measure the probe, so measure the quadrature of the harmonic oscillator that corresponds to the probe, and then we get a point of a J of omega. And then we have to repeat in order to get all the value. So here, actually in blue, you have the analytical calculation, and in purple, you have the exact method, so what is going on in theory if I apply the probing technique by looking at the excitation of the probe harmonic oscillator. What we need to implement experimentally in order to implement this kind of transformation, so in theory we need something which is really, in a way, single mode, in the sense that we need to have, so here what I'm showing are the diagonal elements of the squeezing matrix that I have to implement. And you see that here you have just one value which is really squeezed. So normally, if I don't do pump shaping, in the sense that I just consider a Gaussian shape for the pump in my experiment, what I can get is this kind of spectrum of value for squeezing. So if I try to optimize it, what we can get, for example, these are two different optimizations for the different crystal lengths. We can get something in which we can really have one mode which is more squeezed than the other, but really having all the other modes with zero squeezing in our actual experimental setup is quite difficult. We have really a multi-mode scenario. And then you can look at which kind of basis change you need and to which kind of local oscillator spectrum correspond. And here, for example, I'm showing for one particular optimization for the three different environments for three different frequencies of the probe, the kind of shape that we have to do. This is another kind of optimization. And actually, this is kind of shape that we can really experimentally produce in the setup. So what are the results of simulation? So here you have a lot of plots, but just look, for example, in the lower part. So here, I mean, again, I'm just considering the analytical calculation in blue. The violet, the purple circle are the exact methods. So if I apply exactly the probe method, what I can get. And the other three curves are three different optimizations for the pump shaping. So what I can get in the experiment, considering experimental value. So here you can see that actually the raw value of the J omega is quite far. But if you can take the normalized version, I mean, we are really able to reproduce the shape. In the sense that given the tree network, implementing the probe technique, you are able to recognize the tree that are different. And actually, this discrepancy comes from the fact that actually we are really not able to have one single mode which is squeezed and all the other to zero. But in principle, it can be done. So then I was showing some kind of network that, yes, I mean, this is not complex. This maybe has some kind of complexity. This is a random network. I mean, you can argue maybe it's not really complex. So we try to show other kind of more complex networks. So this is another class of random network, Barabasi-Albert. Then you have this, what Strogat would describe kind of small world network. And then we played with some real social and biological network that you can find in some repository. So here is, if I'm not wrong, this is some of the connectivity of the brain of a cat, or I mean, something like that. And here you have the social network of dolphin. And we really try to reproduce, I mean, the kind of environment of the harmonic oscillator in our case, just to show that we are really able to reproduce any kind of topology, which is really a complex topology, as the complex topology is defined in network theory. Well, okay, I was promising something like a network made by 50 nodes. But if you remember, I mean, in principle, we have more than 50 modes in our experiment that are squeezed and that we can use for making this reconfigurable implementation. But if you remember, I was saying that also for the cluster state, we are just able to have 12, 16 modes in the cluster. So this depends on the fact that actually our limitation is more a technical limitation that's come from the detection part, in the sense that the local oscillator is not large enough, the spectrum is not large enough in order to detect all the high-order modes which have larger and larger spectrum. But we have working process in order to have a coherent broadening of this LEO spectrum in order to use it and having more and more modes to make the experiment. And then, this is more an outlook, so I'm coming to the end. Well, there are other strategies that we can use to get more. For example, the idea is to merge strategy which consider mode in the spectral domain and mode in the temporal domain. If you know actually the experiment of Furuzawa group building cluster state, the idea is to merge a little bit the two framework. And a last part, which is quite important in a way, is to introduce non-Gaussian operation. So in particular, what has been done in our laboratory very recently is the implementation of coherent mode-dependent single photon subtraction. So single photon addition and subtraction are kind of non-Gaussian operation, which can be implemented probabilistically in our setup. Because as far as you stay Gaussian in our setup, we have deterministic generation of all the kind of complex network as I was showing before. But if you want to introduce some easily, in a way, some non-Gaussian statistic, you have to use probabilistic process. But this is kind of interesting probabilistic process. So the well-known way of subtracting, for example, a photon from a light field is to use a high transmittivity beam splitter. And then you have a single photon counter on the reflected port. So every time you see a single photon on this reflected port, you know that the transmitted state, has one photon less. So you have subtracting one photon. So here we want to be mode dependent, actually, because we want to be able to subtract a photon from a particular mode. We want to control the non-Gaussian property of our multimode state. And then you can do that by using a nonlinear process, which is up conversion, in which actually you up convert your state with a gate beam, which has a particular shape. So which means that every time you see one up converted photon, you have subtracted a photon from the signal on the mode which depends on the gate beam. So you can do that by playing with the nonlinear process here. And something which is interesting, you can also try to subtract a photon from a combination of modes, from a superposition of modes. So this is the reason why the name is coherent. And so in the framework of quantum complex network, this is interesting because, if you think about complex network you want to use for making some quantum information processing, of course you need some non-Gaussian part, because the Gaussian part is not enough. And also because you can think about as having this non-Gaussian particle-like, in a way, perturbation on this complex network, and then try to think about how to have a sort of quantum transport of this non-Gaussian particle in this kind of complex network. Okay, I think that's all, and I would like to thank you for your attention.